Welcome to this course on path integral methods in physics and finance. This is brought to you by IIT Roorkee under the NPTEL program of the Government of India. In this course, I propose to cover the general theory of path integrals. Path integrals have been applied to a spectrum of applications. We have applications in physics. We have particularly deal in the context of quantum field theory, quantum mechanics, statistical mechanics. Path integral also finds applications in the field of finance. I shall be talking more about them. Path integrals in Euclidean space are of general interest, but they are also relevant when we discuss path integrals in Minkowski space, because there is a relation which is called Wick rotation, by which we can move between Euclidean space and Minkowski space. Then I propose to cover, when I talk about the applications of path integrals in physics, I propose to cover the applications or the derivation of correlation functions, Green's functions in the context of scalar fields and gauge fields. We shall also try to talk about renormalization and in particular the Wilsonian renormalization scheme, and finally towards the end of the course I will take up applications of path integrals in the field of finance in the pricing of derivative products. The recommended text, well, the master craftsman in the field of path integrals is none other than Richard Feynman. Together with Mark Kac, Norbert Wiener and Dirac, Richard Feynman is credited with the development of this instrument or this tool for the various applications that I have just enumerated. So, Richard Feynman's text together with Hibbs and Steyer called Quantum Mechanics and Path Integrals 2010 edition is a wonderful text. We have a text by the name of Path Integrals in Field Theory by Mossel. Louis Ryder's textbook on quantum field theory is quite comprehensive and also quite pedagogically very attractive, very convenient for a beginner. So, Ryder's book on quantum field theory I shall be using. Then there is a book by Kleinert on path integrals which talks about the applications of path integrals in various areas, in statistics, in polymer physics and also in financial markets, together with of course the standard applications in quantum mechanics. The course utility, well, basically when you talk about quantum mechanics, there are two fundamental approaches to the development of quantities of interest in quantum mechanics. One is the canonical quantization scheme and the second is the path integral formalism. Path integral formalism is relative compared to the canonical scheme, which has a more of a formal structure. Path integral approach is more explicit. It brings out the relationship between the classical mechanics and quantum mechanics. In particular, when we talk about path integrals, when we do the integration, path integration, we continue with C functions, or we do not use operators within the integration, unlike what we have in canonical quantization. More about this when we talk in detail about path integration. String theory, which forms the contemporary candidate for the unification of the four forces, the gravitation and electroweak force and strong force and electromagnetic force, is again based on largely on the path integral formalism. With the development of financial markets across the world, newer and innovative financial products are gradually entering the market, entering the stage marketplace. The fair pricing or approaches to arriving at a fair price of these innovative instruments having having diverse payoffs, having payoffs which are based on the path that the underlying takes to up to the maturity of the instrument is becoming more of a challenge. Path integrals have also contributed to the development of this free pricing or the fair pricing schemes. As I mentioned earlier, the formal structure of path integral was largely developed by statisticians Mark Kac and Norbert Wiener. Wiener also is better known in fact in the context of the development of the statistics of Brownian motion, but nevertheless he has also worked on path integrals. Mark Kac has been associated with the formalization of the structure, but the basic use of this path integral formalism as a toolbox was initiated by Richard Feynman. He put it on a very strong pedestal and he used it extensively for developing this alternative formalism of quantum mechanics and quantum field theory using the path integral approach. As I mentioned, path integral finds applications a huge spectrum of applications, and this application spectrum is growing by the day. Quantum field theory constitutes the primary application area. We also have statistical mechanics and, as I mentioned, string theory, which is really an extension of quantum field theory from Minkowski space to curved space time. Condensed matter physics, stochastic processes, polymer physics and financial markets are some other applications of path integrals. Now, the motivation for this course, that is very interesting. To understand the motivation for this course, let us go back a bit. Let us go back nearly 100 years. In 1927, there was a publication by Davison and Garmar in the Physical Review in relation to the diffraction of electrons by a crystal of nickel. That is more famously known as the two-slit experiment. Let us try to understand the physics behind this two-slit experiment. Before we get into this, let us look at this particular slide. We have a stream of water flowing, there is a gradient and the stream of water is flowing along that gradient, and then it encounters a dam or an obstacle or an impediment in which there is a small slit. And we examine the pattern of the flow of water beyond the slit. As you look at it, the slit tends to behave like a source of water, and from here then the spherical waves of water tend to diverge and tend to move forward in time. If you look at this in the background, there is a more or less uniform intensity formed on a screen, you may say, or an observation point reflecting that the waves are moving more or less steadily across the length of the stream, but diverging spherically outwards from the slit. Now, let us apply this analogy to a more sophisticated setting. We have two screens. The screen on the extreme left is a detector screen, where we have arrangements by which the collision on the screen by a particle can be detected. In front of that, there is another screen on which we have two rectangular slits, vertical rectangular slits. Electrons, or for that matter any classical particles to start with, are bombarded from a gun, electron gun for example, onto the first slit. Let us call it slit A, and let us call the detector slit the slit O, and let us call the source of electrons, the electron gun, let us call it S. Now, electrons are bombarded from the source S onto the screen A, which contains the two slits, vertical slits of very narrow dimensions. Some of the electrons may collide with the opaque part of this screen and fall back. Some of the particles may go through the slits. Now, if the world was classical, then what we should observe on the screen would be two bands corresponding to the electrons, which move away from the slits and collide on the screen O. From each of these two slits would act as a source in itself, and beyond that the electrons would form two uniform bands. That would be the situation, or that would be the expected situation if the world was to be classical. Now, let us see what actually happened in the experiment. What actually happened in the experiment was radically different. When the electrons were shot into this screen and they moved out of the slits, instead of getting two well defined bands corresponding to each of the two slits, one corresponding to the left hand side slit and the other corresponding to the right hand side, a set of bands of different intensities were observed on the detector screen. We had a central band which was of high intensity, then two areas of darkness, and then again bands, and then again two areas of darkness, alternating areas of darkness and bands, very similar to what we have in an interference pattern. So, what does it imply? It does imply that the electrons that are moving out from the screen are in some sense behaving like waves, and these waves of electrons are the two sets of waves moving from the two different screens. As they move out of the screen or out of the screen A, they interfere with each other, giving rise to the bands on the screen O. The observation becomes, here we see the same experiment using laser light, and again we see regions of darkness and light colored blobs on the screen, showing that there is constructive and destructive interference. Now, let us try to understand what is happening. So far, if you look at this, instead of having, let us go back to the water wave experiment, and instead of having two slits now, one slit, we now have two slits. Earlier we had one slits and we had one mark of uniform intensity, one pattern of uniform intensity on the background. Here we have got two slits now. Water is flowing at a gradient from away from the screen into the two slits. Now, as you can observe, when you move away from the slits, water that is emanating from or moving out from the two slits is interfering among each other. The two slits, the water passing through the two slits is interfering with each other, and we are getting regions where there is minimal vibration, minimum waves, and there is regions where there are maximal waves, very much like interference, standard interference. And the image on the foreground, as you can see, consists of bands of dark and light bands corresponding to constructive interference and dark bands corresponding to destructive interference. It is pretty much similar to what we had in the case of two slits when electrons were made to bombard on the screen using the electron gun. But then something very interesting happens. Now, so far so good, but now suppose we release the electron, or the electron gun releases the electrons very slowly, one electron at a time. Let us say we release an electron or a photon for that matter at intervals of 1 hour each. then even then what happens is the bands continue to be observed. That is very intriguing, that is very challenging to understand. When there were two sets of beams, one could understand that waves are being created out of the two sets of beams, and those waves are interfering, and therefore we are getting this this pattern on the screen. But now what is happening is every particle or every electron is moving, is being hit or is being focused as single units, one electron at a time. One electron at a time passes through the slits, and in spite of that we observe the pattern, we continue to observe the pattern. Now it could be possible, for as a thought process, it could be possible that the electron splits up into two parts. One part goes through one slit, the other part goes to the other slit, and then this interference pattern arises due to the interference of the two waves that emanate from the two slits. But it is in that case, were it to happen that way, then the intensity of the interference should have reduced to half of what it was earlier, but that is not seen to happen. And in fact, it is observed that when one electron is made to pass through the slits, it strikes the screen O, the detector screen, at only one point, not two different points. It strikes the detector screen at only one point. So that is very interesting, that is very challenging. So that means what? That means that one single electron, which was emitted as a particle by the electron gun, somehow behaved as a wave during its passage from the electron gun to the detector screen, and resulted in the formation of this interference pattern. So let us summarize what the implications or the inferences, observations of the two slit experiment. If you have only one slit open, then there is no interference, you see only a one single band on the detector screen O. If you only open the second slit, only the second slit, again the same thing happens, you get only one single band, there is no interference. But if you open up both the slits, then interference pattern appears. And in fact, if you slow down the emission of electrons from the electron gun to the extent that you release one electron at a time, then even then you find that the interference pattern is retained, and secondly, there is no fall in the intensity. One electron strikes the screen at only one point. So that is the anomaly which is created by the phenomenon of quantum mechanics, and that is in a sense the motivation for that clicked in Feynman's mindset, that resulted in his formulation of the path integral formalism of quantum mechanics. Let us see how he went about it. What was Feynman's line of reasoning? Let us try to understand. You see, when we had electrons passing, when we had an electron or a stream of electrons passing through a screen A with two slits, let us call them slit A1 and slit A2, then emerging from the two slits A1 and A2, we found that on the screen O, we found interference patterns, and these interference patterns was created by the sum of the amplitudes of the waves arising from, emanating from these slits A1 and A2. So given any point on the screen O, the amplitude at that any arbitrary point on the screen O, the amplitude at the arbitrary point O would be given by the sum of the amplitudes of the matter waves that move through the screen A1 and the amplitude of the matter wave that moves through the screen A2. the sum of these two amplitudes will give you the amplitude at that particular point under investigation on the screen O. That is the standard formalism that we have in the case of wave mechanics. Now, what happens? Suppose we have a third slit. Let us have, instead of having two slits on the screen A, we have 3 slits on the screen A. Then naturally, on any point on the screen O, the amplitude of the wave hitting that screen would be the sum of the amplitudes are due to the waves passing through slit 1, passing through slit 2 and passing through slit 3. In other words, they would be represented by summation I equal to 1, 2, 3, the path through slit A, amplitude of the wave passing through slit A, amplitude of the wave passing through slit A2 and amplitude of the wave passing through slit A3, and so on. If you further increase the number of slits, obviously the summation would increase gradually. But the point is let us go back again. So, that means what? That means if you increase the number of slits at any point on the screen, the amplitude would be given by the sum of the amplitudes of the waves that pass through the various slits. In other words, two-legged paths that start from the sources, hit any of these A's and then move to a point O on the screen. Now, what happens? Suppose I put another screen B between the screen A and this detector's screen O. There is no necessity, there is no mandatory requirement that the paths that we are discussing or the paths that we are talking about must necessarily be two-legged paths, S to A and then A to O. That is not necessary, that is not codified. You can have another screen B between A and O, and in that case what will happen? The paths would have to move through O to A to some slit in B and from some slit in B to the detector screen O. And in that case what happens? In that case the amplitude at any point O on the detector screen would be given by summation I j, where I and j AI are screens on the AI are slits on the screen A and Bj are slits on the screen B. So, any particular wave will first start from S, move to some slit on screen A, from there move to some slit on screen B and then from there move to the point under reference, that is on the screen O. So, instead of 2, it now becomes a 3-legged path. But again, it is not at all necessary that you confine yourself to 3-legged path. So, you can have another screen C between say B and O. That was Feynman's reasoning. So, what Feynman said, that now suppose I increase the number of slits and make them approach infinity, what happens then? If the number of slits in any screen, approaches infinity, what happens to the screen itself? The screen simply disappears. Okay. So, in the limit that I tends to infinity, the screen simply AI or screen A simply disappears. Then similarly, if the screen B also has infinite number of slits, what does it mean? It means that the screen B disappears. And if the number of such screens with infinite, each with infinite slits is increased to infinity. The number of screens is infinite and each screen has infinite number of slits. Then what happens? Then all the screens disappear and there is vacuum between the source and the detector screen, the source S and the detector screen. Therefore, what I am trying to say is, in the limit that the number of slits in each screen tends to infinity, that is I tends to infinity, j tends to infinity, k tends to infinity, and the number of screens also tends to infinity. Each screen disappears, the number of screens is all are infinite, all are having absolutely infinite number of slits, so all disappear, and the number of screens is also infinite. So, it does not it implies that both the things together imply that there is absolutely nothing, there is total vacuum between the screen A between the source S and the detector screen O. So, that being the case, in that situation, what do we have? We get the dynamics, or we get the relationship between the object that starts at O and the amplitude due to the object that is emitted at the source S and that is detected at the detector's point O. Putting it in another way, what we can say is that the amplitude at the detector point O is the amplitude of all, is the sum of the amplitudes of all paths which start from the sources and end at O. That is what is the formalism of path integral. So, let us summarize what we are saying. To obtain the amplitude of the wave function of a wave particle at a detector point is on the screen O, emitted from a point source S, we have to sum the amplitudes of particle waves propagating from the source to the detector, following all possible paths between the source and the detector. This is the most important component, following all possible paths between the source and the detector. So, that being the case, if you do the summation of amplitudes across all possible paths, you are in a sense working out the dynamics of the system, which is comprising of the release of a particle at the source S and the detection at the detection screen O. Now, it is very often the case that it is argued that quantum effects predominantly make their manifestation, predominantly appear in the context of microscopic objects, electrons, photons or quarks and so on, objects which are microscopic, instead of at a large at a macroscopic level which we encounter in daily life, for example, a cricket ball or a billiard ball or whatever. We do not tend to feel the impact or the presence of quantum effects in these kind of systems. So, let us try to understand why this kind of thing happens. Let us know what is quantum mechanics. Quantum mechanics says that all objects in this universe have a dual nature, that is, they have a wave nature and a particle nature. Both of them simultaneously exist in every particle. So, sometimes the object behaves like waves and sometimes the object behaves like a particle. But the important thing is that quantum effects are universal. Quantum effects or dynamics of all bodies, all objects, whether they are microscopic, whether they are macroscopic, whatever dimensional they are, the dynamics are governed by quantum laws. It is only that in certain cases the approximation provided by classical laws is good enough for our visualization for our understanding. And classical mathematics or mathematics of classical mechanics being simpler, we tend to use it because we are comfortable with them, we are adequately satisfied by using classical mechanics. So, the bottom line is quantum effects are invariably present, but we may not actually observe them. There could be why we do not observe them. There is a logic behind, there is a rational. First of all, what is a quantum effect? Classical mechanics views objects as particles, and it develops the kinematics of the system by assuming the objects as particles. So, therefore, if quantum mechanics are to be observed or are to appear, then it must necessarily be that some wave like characteristic of the system should be predominantly or should be visible, should make its manifestation very conspicuous, and then we can say that quantum effects are present. I repeat, classical kinematics are based on the particle nature of objects. Quantum mechanics says that objects have both both particle and wave nature. So, if you want that quantum effects should supersede classical effects to such an extent that they make that they appear very conspicuous, then we must say that these wave like characteristics should manifest themselves prominently. That is the important thing. But why it does not happen, that is what we need to understand. Now, in a macroscopic system, a macroscopic body is comprised of a huge number of minute objects. When we are talking about a huge number of minute objects and they are behaving randomly, the wave characteristic or the wave nature of these particles, despite being present, the orientation is such, the phasing is such that on the average they cancel each other, and as a result of which, when we look at the object in totality, the macroscopic object in totality, it seems that the quantum effects are not there. If there were some mechanism, or if in a certain situation the quantum or the quantum waves or the matter waves corresponding to the constituents of a macroscopic object orient themselves in a particular manner, which technically is called coherently. If they organize them coherently, these particle waves, then even in the macroscopic domain we would be able to view and perceive quantum effect. So, that is the important thing, because these matter waves in the case of macroscopic objects tend to annul each other, tend to cancel each other, because they are randomly oriented, randomly phased. Therefore, on the average, on the overall, when we look at a macroscopic object, we find that they are not present. However, in coherent situations where these objects are present in a coherent manner, we can observe them. And take a brief example to illustrate this. Let us say the impact of coherence. Let us say we have got 5 die and we toss them. So, there are only 6 possibilities that all the 5 die behave in such a way or turn up in such a way in a random experiment that they are aligned in a particular manner, with all showing the same figure on the top. However, how many ways can they be disoriented if with different numbers on the top? Because there are 5 dice, the total number of possibilities is 6 to the power 5, and if you eliminate the 6 possibilities of coherency, then the number of possibilities where there could be different numbers on this on each die on the surface of each die would be 6 to the power 5 minus 6, which is huge, which is much larger than 6. So, that is the reason that coherency is an exception, it is not the rule. The rule is that the randomness tends to annul each other, the randomness in phase, the randomness in orientation tend to annul each other, and on the average the matter waves do not seem to exist at all. We will continue after the break. Thank you.